working with extremophiles. Right? That was what you were working before. So you said that they live obviously in extreme environments, and so they have to put up with a lot of DNA damage. And so what kind of environments? Like, is it UV? Is it extremely hot, extremely cold? What kind of environments were you looking at?
So I'll tell you, the organism that caught David's eye was one that grew at between 55 and 65 degrees centigrade. So that's 131 Fahrenheit and up, maybe to 138, 40, something like that. So that's very hot. And, and it grew, and it wasn't like small growth. This was rapid growth at that temperature. But we've also looked at other organisms. For example, the one that's in the Aeonia line that David and I worked on actually survives and grows under UVC radiation, which is phenomenally, it's phenomenal. The fact that it's constantly getting bombarded by radiation that is used to kill bacteria and break down DNA, is mind-blowing. But we've also been, in environments where it's really cold. I went down with some staff scientists 5,000 feet below the surface of the earth in an abandoned gold mine to isolate organisms in high redox environments. So things with a lot of iron it's pro-oxidant and leads to free radical formations. And yet somehow these organisms grow and thrive and can protect themselves from radicals that would normally be detrimental to non-extremophiles. So I cover the whole gamut, high salt, low pH, high pH, UV, temperature. And it's in a very exciting field because you don't know what you're going to find. So that's what I cover.
Yeah, interesting. So you did find this one, well, or Dr. Sinclair and yourself found this one that NASA was looking at. So could you talk about that bacteria and the one that was withstanding UVC?
Yeah, so backstory on that. So David and I actually first got involved with NASA, I believe in 2017 or 2016, where we were looking at how to protect the astronauts' genome while they were going to Mars. So the problem here is not necessarily engineering. People always think, oh, it's the rockets, oh, it's the life support, this and that. It's actually our own bodies that are one of the main bottlenecks for space travel, because once we're outside of the protective atmosphere of the Earth, we're constantly bombarded by high energy particles that will lead to Alzheimer's, dementia, eye problems, DNA damage, accelerated aging, cancers. So, David we submitted this packet for using a small molecule to help upregulate DNA repair mechanisms to help mitigate DNA damage during long duration space travel. So while that was happening, I was working with a group called Planetary Protection. It sounds science fiction and out of this world, and it is, but Planetary Protection's goal is to make sure we don't contaminate planets and planets don't contaminate us. And one of the things they were looking at were novel organisms that were on the space station, whether they were in the water systems or just on the environment, and also ones that were in their clean room. And they found an organism in their clean room that survived germicidal lamp exposure. So the NASA scientists were like, hey, I wonder if it can survive space radiation. So they shot it up to the space station and put it outside the space station for 18 months. And then the astronauts took it back, worked on it a little bit, and then sent it back down to the Earth. And NASA found that the organism was still viable. It still was able to grow. And not only was it able to grow, but it had more resistance than what it had previously. So NASA took this and, they patented it and they put it away. And then because we were working with them and we were kind of in like this quasi-commercial government space, they were like, hey, do you think you can do something with this? So David and I were like, yeah, of course. Let's look at it for a sunscreen. So we brought it into our lab. We worked on it for a year and a half. And we found that it had amazing UV absorption properties, UVC, UVA, UVB, even all the way out to IR. And we were like, okay, let's commercialize this. Let's go forward. Let's put it in sunscreen because people are worried about the filters. They're worried about the coral reef. They're worried about the endocrine systems and all these other things that are being affected by sunscreen ingredients. And then we found out, in the US, it's a drug. And it takes 10, 15 years to make it a UV filter. Right. So instead, we use it as an SPF booster. So you add it to already approved sunscreen formulations, and it actually enhances its SPF factor. So that's kind of a little workaround to still get it in sunscreen. But at the same time, David and I were contemplating what type of repair mechanisms, what type of machinery must this organism have to protect itself from cosmic radiation? So we went back into the longevity, anti-aging aspect and started studying it, looking at it. We found out that it makes these compounds that actually accelerate and activate sirtuins, right? Sirtuins are DNA repair enzymes. So the bacteria produces a compound that actually activates and accelerates sirtuin activity. We also found out that the organism produces compounds that enhance our cells' ability to produce hyaluronic acid intrinsically. Now, this is groundbreaking because in the cosmetic world, people put hyaluronic acid on your face and you hope it absorbs in through the skin and gets to the matrix and binds water. The problem is hyaluronic acid is big and the absorption of it is dependent on the size. But guess what? The amount of hygroscopic ability or ability to bind water is also dependent on its size. So the smaller you go to penetrate the skin, the less water binding you have. But so this compound actually tells your body to make more of your own hyaluronic acid. So you don't have to worry about dermal penetration or water absorption. And what's better than your own natural hyaluronic acid, right? And then we looked at antioxidant capabilities. We looked at other enzyme functions, and we were like, wow, this is crazy. Like, not only is it good for absorbing UV and doing this, but it has all these other benefits that could really help your skin. And that's when we decided, you know what, okay, we'll focus on, SPF boosting and stuff like that, but let's focus also on making a product that people can use today to help their skin at a different way than what is currently on the market. So that's the story in a nutshell, as fast as I can give it.
Can you tell us what the microbe is?
Sorry. Yeah, it's called Bacillus pumilus.
Right.
It's so Bacillus pumilus is ubiquitous, right? Bacillus in general is ubiquitous. It's all around the world. But what's interesting is that this organism had constant environmental stresses put on it for 20 plus years. So that's the difference, right? Mm-hmm. So it adapted in a way to thrive in an environment that would be detrimental to everything else. And through decades and decades of growth in stresses, it basically was able to adapt to the environment. So, you can find Bacillus pumilus everywhere, but the properties are not there. And we've looked to see, obviously you can't survey all of them, but in general, you can't find, the properties here are very unique, which is what allowed us to, patent it and what allowed NASA to patent it and how we control it. And even the way we grow it now is trade secret, right? The organism is produced at scale in France. We produce 5,000 liters at a time. We're looking to go up to 15,000 liters. But all of that growth technique is proprietary trade secret, something that we developed here in our labs that help maintain the phenotype or the properties of that organism.
Right. And then you don't use the actual organism. You use the lysate, right? Could you explain what the lysate is?
Yeah. So what the lysate is basically a specific extract from the bacterium. So we grow the bacterium in a certain condition that promotes the production of these beneficial compounds, much higher than under standard growth conditions. And then we kill the bacteria, we lyse it, and then we pull out very specific components that are beneficial for that. It's so it's basically lysed, the bacteria is lysed. We don't use a live organism. And a lot of people think, because of the way things are advertised in the cosmetic world, that it's a probiotic, but there's no live bacteria in our products because there can't be, right? In order to go on the market, they have to have antimicrobials and preservatives that you can't have more than 100 cells CFU per mil in the product. So you can't have a probiotic like in a yogurt that has billions of cells. It wouldn't comply with what's required.
One last question on the microbe. So it survived in UVC and it absorbs a UVA-BC. So did it protect itself by absorbing the UV radiation or repairing its DNA, or both?
Yeah, so this is actually very interesting. So when it was put up outside the space station, it was in its it was in a dormant state, right? But it still had a way to protect its DNA. So the organism actually secreted this kind of milky white substance around itself. And we believe there are also these really cool proteins that encapsulate the DNA that minimizes radiation damage. So whether it's absorbing in a resonance structure, like just bouncing it around, or whether it's actively deflecting it, we're still researching. But the fact that it has these properties that have been identified by NASA, it's published, you can find the papers, that it produces this milky substance that coats it, that they believe helps block and absorb the radiation, has these proteins inside of it that help protect the genome from this radiation. And then, of course, the compounds that actually accelerate or activate sirtuins would have one believe that any damage that did occur to the genome would be rapidly repaired when your organism grows, because its lysate and components inside activate DNA repair enzymes. So it's kind of like a two-part system is what we believe is happening here.
Interesting. It is amazing. I mean, it is an amazing, amazing microbe. So this product and the microbe are both space certified. So can you talk about what that means?
Yeah. So NASA will never endorse something itself unless it's a T-shirt or a mug. You're not really going to be seeing the NASA logo anywhere. But there's this forward-facing group called the Space Foundation. That's a nonprofit part that is more the public face for promoting NASA-developed technology. So an example is Tempur-Pedic mattress. Okay, most people know what Tempur-Pedic mattresses are, but they don't know that Tempur-Pedic mattress was actually the cushion used on the space shuttle. So the astronauts were sitting on a Tempur-Pedic mattress to absorb the forces of launch. And then they decided and realized, hey, this would be a great mattress. So when they brought it out, Tempur-Pedic mattress was actually certified space technology because it was used and developed by the space program. The Bacillus Lysate is certified space technology because it was researched and developed by astronauts on the International Space Station. Yeah, the initial concept wasn't for cosmetic applications, but the fact that it was federally funded, went up to the space station, researched by astronauts, brought back down to drive the science in the aerospace industry, allows it to be certified space technology. And that is, no other cosmetic ingredient or product is certified space technology. And, some people may think of that as a marketing ploy, but I just think of it as being really cool and help validate the story that this is actually NASA research. This is actually space research, from the International Space Station.
That is cool. Yeah. And also, what I guess I didn't realize before was that it was actually formed during that period while it was sitting outside the space station. So it was, I guess the microbe evolved under those conditions.
Yeah, I don't know if it evolved per se, because it already had the ability to block block UVC radiation on Earth. It just wasn't as prevalent. So I think what happened, honestly, is that when the organisms were put outside, remember, they're putting millions, if not billions of them outside in a Petri plate or in a tube or whatever. I believe it selected for the most resistant ones. So it killed off all the low resistant or medium resistant, but it held on, it allowed the more resistant ones to outgrow and actually become differentiated from the other population. Because in general, you always have tolerance issues, right? Like you have some that are super tolerant and some that are not tolerant at all. And if all of them are growing happily together, the distribution of them may not be to one side or the other. But if you put them in an environment that basically kills off the less efficient or effective ones and isolates and promotes the more resistant ones, you're going to end up with a more resistant population. So I honestly think that's what happened on the space station, but we would have never selected for those here on Earth unless you put it in like a simulated cosmic radiation beam, which there is one, but it's not the most efficient thing to use instead of just putting it outside of the space station, the Columbus module, which,
right.
That's full spectrum too. That's cosmic radiation. That's everything from X-rays all the way to UVC. That's like every type of radiation you can imagine. So it's pretty exciting that it survived.